gentlemen, it's my great pleasure and honor to introduce you Professor Ghamouss. Professor Ghamouss joined MSL UNSXP in April 2022 as an associate professor, where he leads a research group focused on energy transition with key areas including hydrogen production and utilization, as well as electrochemical energy storage systems such as batteries. He brings a rich experience from both academia and industry, having also worked as a researcher in engineering at the EDF in France, developing membrane electrode assemblies for metal air batteries. He's an author and forwarder of 80 publications. He has 8 patents and has provided more than 30 PhD theses. He contributes to electrochemical storage, hydrogen technology, and material science. So Professor Fouad has also played an important role as a scientist expert for the French National Research Agency and served as an elected member for the French National Council. So please join me in welcoming Professor Fouad. So Professor Fouad, the floor is yours.
And I will start my talk, because I understand we are late. So the title of my talk is Electrochemical Conversion and Storage, from the concept to the application. So I will start by some basics of electrochemistry, fundamental. Then I will move forward in my talk talking about batteries, mainly lithium-ion batteries, by different aspects, because I know that you already had to talk on batteries, lithium-ion batteries, by Professor Sadoun yesterday, and this morning Professor Mouad was talking on sodium-ion batteries. So my talk will be different, I guess, regarding what my colleague has presented. And I will also give, there is a part on, where I will talking about supercapacitors, the concept and their utilization. And the last part of my talk, if we have time, we will talk about hydrogen production by electrolysis. So electrochemistry involved in conversion, energy conversion. Electrochemical reaction convert chemical energy to electrical energy by special reaction that provide or use electrons. So in one way, with electrochemical reaction, you can generate electricity. That's why we are using it in batteries, in fuel cells. Mainly those reactions are spontaneous, meaning that the Gibbs-free energy is negative, and those reactions don't need any external activation. So they can you don't need any activation and provide electricity and energy spontaneously. And then in the opposite, electrochemical reaction can also be forced to work and to be done. This is why we call electrolytic cell. A cell where electrochemical reactions are forced to happen. In this case, the reactions are not spontaneous, and this is the case in hydrogen production by electrolysis and water splitting. This is an example of a cell, electrochemical cell, where you have a cathode and anode. On the anode side, you have the oxidation of water, and then the reduction of water providing hydrogen on the other side, the second side. Galvanic cell, which provide electricity. Some examples include batteries and fuel cells. And of course, battery, there is different chemistry. As you know, the storage of electrical energy directly is not possible. We need at least two transformations. You need to transform, the first transformation will be dedicated to transform the electricity provided by the source. Here I give an example of renewable sources. So you provide the renewable sources will provide electricity, and this electricity should be converted to another form that will be storable. And then a second transformation will allow recovering this energy again. This is what happened exactly in batteries when it's discharged. We charge the battery, provided to the battery electricity, and this electricity will make the first transformation, which is electrochemical transformation, in this direction, or the direct direction of the reaction. And this is what we call the charge, the reaction of the charge. And once it's charged, then if we short circuit both sides of the electrode of the batteries, then we can discharge the batteries. And once it's discharged, if it is secondary batteries like lithium-ion batteries, we can charge it again. So we can also, this is one way to store electricity and recover it. Another way to store electricity is to use this electricity to make electrolysis of water to produce hydrogen, and then this hydrogen, if you don't need it immediately, you can store it, but if you need another time, you have a need of electricity, then you can use fuel cell to produce electricity using this hydrogen. And of course, if this hydrogen is produced by a source of electricity which is renewable, and it can be considered as green hydrogen, of course. So the first part of my talk will be on batteries, and then I will move forward to supercapacitor. The both systems are similar because both contain two electrodes separated by an electrolyte. But the similarity stops here, because in batteries have really electrochemical reaction. In at least in conventional supercapacitor, you don't have any electrochemical reaction. So by mistake, some people call it electrochemical supercapacitor. It's not true, because there's no electrochemical reaction in supercapacitor. In conventional supercapacitor, of course, I will be talking also on other kinds of supercapacitor, including some active materials, and what I call active material that can provide electron by charge transfer and by oxidation and reduction reaction, or electrochemical reaction. This is a Dragon plot showing the main system, the main electrochemical storage system, and the comparison in terms of energy density and power density. And of course, if we need energy in this side, batteries of course provide more capability to store energy. If you need power, this side, and this time we will look at a system like supercapacitor or ultracapacitor, depending what you name it. And there is a particular case in supercapacitor. This is what we call pseudo-capacitor or hybrid supercapacitor or asymmetric supercapacitor. And those ones have in their composition active material similar to what we can find in batteries. And the advantage of those systems, hybrid systems, they can provide, of course, more power than battery, because they are supercapacitor. I will explain why, and more energy than conventional supercapacitor. In batteries, you have different chemistry, and what we mean by chemistry is the composition of the material, the active materials at the electrode, and also the electrolyte. There is two main families: aqueous batteries, like conventional one, that I'm sure you know already, lead acid batteries, nickel cadmium, nickel metal hydride. Those batteries use aqueous electrolytes between the electrode. The second family are batteries that are use organic electrolyte. mainly the famous one is, of course, lithium-ion batteries. And even in lithium-ion battery, you have different chemistry. And the difference between those batteries are the composition, the nature of the material, the structure of the material, the composition, because all the cathode material in lithium-ion contain mainly metal oxide, and this transition metal oxide and dissolution metal oxide can be different in terms of nature and composition. And the anode side also can use different anode material in lithium-ion battery. That's why there is very different, a lot of different chemistry. Some of them are more specifically designed to provide high power or high energy. And recently, we have also this kind to be considered all solid-state batteries. Those batteries don't contain any liquid electrolyte, and this has the advantage to ensure more safety for the lithium-ion batteries. Maybe it's not necessary. What is oxidation and reduction? One of the old definition is oxidation is the gain of oxygen, and reduction is the loss of oxygen. Oxidation of iron is due to the corrosion, and the presence of humidity is an oxidation reaction. Burning of butane or any other hydrocarbon is an oxidation, and because the molecule is then after the reaction is combined to oxygen. Another definition is creating the bond between the molecule and or the atom and the hydrogen. Once it's getting hydrogen, we can call this in this way the reduction. And if it is releasing hydrogen, the molecule is being oxidized. There's two definitions. But when you look to other reaction, we look to this oxidation. Obviously, this is an oxidation because sodium is reacting with oxygen, forming then this oxide, which is an ionic oxide, meaning that inside this, the species are oxidized, sodium 2+ and oxide ion. This means also that the sodium has lost 2 electrons and oxygen gained 2 electrons. But writing this reaction this way, in this form, we cannot see the electron ion, because the electron goes from one atom to another atom in close contact, and we cannot see this electron. Another remark is to oxidation don't need necessarily the presence of oxygen. So in this reaction, sodium being oxidized and chloride in the reduction to form chloride, and there is no oxygen. So an alternative definition to oxidation and reduction is to use this exchange of electrons to define it. And then we can describe oxidation as the loss of electrons and the reduction as the gain of electrons. Now we can see with this kind of reaction, we can have an exchange and production of electrons in 2 ways, in oxidation and the opposite side in the reduction. This is the previous reaction. Written in or divided in 2 half reaction, where we can see each molecule reacting losing or accepting electron individually, but still we don't see those electrons. We cannot use it. How to use those electrons is what I'm talking about in this part, is to how to arrange this reaction to have a current flow, because if we consider this reaction between zinc and copper 2+, we see clearly that there is a reaction. We can see that the copper solution decrease in the intensity, and the blue solution decrease in the intensity, meaning that we are consuming copper 2+. And in the same way, and at the same time, zinc being oxidized and go into the solution. But we still not see the electron, how to arrange this reaction to get a current flow and to get electricity. See by welding what we call voltaic cell. This is Daniel with the zinc foil and copper foil. So both reactions are divided into half cell to have the complete reaction. So we have half reaction here and half reaction here, and both cells are connected through circuit. This is the basic concept to construct a voltaic cell that provides electricity. And we can read here the voltage generated by this combination, 1.1 volt. And the origin of this voltage comes from the difference of the potential between the two redox couple used here, copper 2 plus copper and zinc 2 plus zinc. If we consider the standard voltage, and we can calculate from the difference here, and we obtain the same, exactly the same value. How we have created here is two electrochemical interface. Then we can give a definition to an electrochemical interface. It's a contact between a solid conductor, electronic conductor, and electrolyte solution, usually solution. But now we know that electrolyte can be also solid as a polymer or ceramic in some applications. At the interface, the reaction will happen. At this heterogeneous interface, the reaction of oxidation and the reduction will happen. So, the conclusion, we have created an electrochemical cell by connecting two electrode and two half reaction in two half cells. And we have created two electrochemical interface. On each electrochemical interface, we have half a reaction. And we can generate voltage by the difference in the potential between the two electrochemical interfaces. Now, second definition, in the Faraday's law, I'm sure that most of you know this law. The Faraday's law gives the direct relationship between the amount of reaction and the current flow. And if we consider the example, the previous example where we consider zinc and the copper, the zinc would play the role of anode in the cell because it had the lowest standard potential, and the copper will be the cathode. And for each half reaction, we can apply the Faraday's law, which say that the quantity of electron, which is related to, which give the quantity of electricity provided by this half reaction, is proportional to the number of mole of electron exchanged or produced during this reaction. Through this formula, this number is the Faraday constant, and then after conversion of Coulomb to ampere-second, we can express this value in this way, ampere-hour per kilogram. This is the unit we are usually using to express the specific capacity in batteries. And we can do the same for the cathode. And if we consider the whole cell, since the cathode and the anode are two, we can consider the anode and the cathode as two electrochemical interface generating electricity, so two generators. So in series, if we want to determine or to calculate the capacity of the cell, the total capacity, then we can make the sum of these two quantities. And of course, energy then comes by multiplying the capacity of the cell by the voltage. Since it is very theoretical, here we can use the theoretical capacity, like here, and the voltage can be simply the difference between the standard potential between the two redox couple. So, seeing the definition, charge transfer is the process happening when at the interface, when species transfer electron to the electrode or getting electron from the electrode. charge transfer across the electrochemical interface is called a Faraday process because it's obeyed to the Faraday's law. And in an interface where there is no electrochemical reaction, but when I have the condition that I have a solid electronic conductor in contact with the electrolyte, we can form what we call a double layer, depending on the polarization of your electrode, positively or negatively. You will have from the electrolyte side, accumulation of anion or cations, depending on the polarity of the electrode. And these two layers form the double layer. And this double layer has capacitors. The voltage here is the drop in voltage between in the distance of the double layer near the electrode. And the other situation when I have a Faraday process, meaning a charge transfer reaction between the species at the solution at the electrode, we can have oxidation or reduction depending on the position of the highest occupied molecular orbital. If it's lower than the Fermi level of the electrode or higher than the Fermi level of the electrode. So we have oxidation and reduction spontaneously. But if the reaction cannot happen, if the Fermi level is higher or the electron level is higher in the electrode, we can apply what we call a polarizer. We can polarize the electrode and change its potential to make this reaction possible. So the reaction electrochemistry can be spontaneous and also forced if the difference of the potential is not good. So this is the same. So now we have two configurations of electrochemical cell, galvanic cell and electrolytic cell. Galvanic cell, like any batteries or fuel cells, provide electricity spontaneously by short-circuiting the electrode, the anode and the cathode. Electrolytic cell, the reactions are forced, okay? Like in electrolysis for water splitting. Now, less complex than what less complex system that we can see in some literature. This is the less complicated representation of the electrical interface of an electrode with electrolyte. You have two cases, of course. One case without Faraday reaction, without charge transfer. So we can simply represent the interface by a resistor, which is the electrolyte, the resistance of the electrolyte, and the capacitor, which corresponds to the double layer capacitance. Okay, and in the other situation, if you have charge transfer reaction, the circuit is more complex. Since we have this charge transfer, which is represented in the interface by this resistance to the charge transfer reaction, and is put in parallel to the double layer capacity. Okay, and the electrolyte resistance remain in the system. And here I didn't consider the mass transport. Of course, if you consider the mass transport, especially for porous electrode or 3D electrode, then we have to add another component to represent this mass transport. And what I want to show you here is that the total current flowing at the interface have two origins. The first one is the Faraday reaction, the charge transfer reaction, and the second one is the capacitive reaction. Okay, so for batteries application, materials are designed to provide mainly Faraday current. For supercapacitor, materials are designed to provide maximum current, maximum capacitive current. So in this case, what we need is simply electrode with the very large surface area. Okay, that's why we usually use graphene, activated carbon. Mainly activated carbon is, in terms of the cost, is more advantageous. Activated carbon that have very, very high specific surface area. And we need also electrolyte, of course, ions on the other side. And for the batteries, we need Faraday reaction that should be very fast in terms of kinetics. Then the charge transfer resistance should be very low. So not any redox materials can be used in battery. It's conditions, but necessary but not sufficient. The material should provide fast charge transfer reaction. In terms of voltage response, this is the response of supercapacitor. It is linear. And following this equation, the term here coming from the ohmic law due to the resistance, mainly to the resistance of the electrolyte. And we have here the response of a battery that's way to, which is fixed by the redox potential of the active material. And we have also the contribution of the serial resistance. Here, R is the electrical serial resistance that includes all resistance in the battery. So here are the discharge and the charge. During the discharge, the voltage decrease, and during the charge, the voltage increase, of course. And the difference here between the two plateaus comes from this side, plus here and minus here. Okay. Another details. I was doing this, but I didn't finish it because it's important to note that a charge or a discharge of supercapacitor takes in general few seconds to minutes. Okay? So I have used the same scale here, but the unit is arbitrary. So here it takes seconds to minutes, and for a battery, of course, it can take dozen of minutes, hours, and so on. So the capacity of the supercapacitor is given mainly by the surface area in contact with the electrolyte and the thickness of the double layer. The thickness of the double layer is mainly linked to the concentration of the charge carrier, your charged species in the electrolyte. Vacuum constant and the electrical constant of your solvent in the electrolyte. So that mainly what can control your specific capacity and supercapacitor, the surface area of your material. In batteries, the charge transfer reaction will provide you all the performances, and the charge transfer reaction comes from the lithium-ion batteries, for example, is coming from the insertion or disinsertion of the lithium in the metal oxide. If you use metal oxide as cathode, by changing its degree of the oxidation, by oxidation or reduction, then you insert or disinsert lithium-ion plus or lithium plus to compensate the change of the oxidation state of the transition metal in the cathode. So this is the charge and discharge, and this is the details the equation that gives the voltage here in the plateau and here in the plateau at the charge. Those terms are the overpotential due to the charge transfer reaction at the cathode and the anode, and those ones are related to mass transport at the anode and the cathode. And the resistance mainly comes from the electrolyte. And as you can see, when I talk about batteries, I use for the polarity of the electrode, I use plus and negative and positive electrode instead of cathode and anode. Because in rechargeable battery or secondary batteries, the cathode and the anode can become cathode and anode, depending if you are charging or discharging. Okay, so this is why usually we use we define the electrode by their polarity, positive electrode and the negative electrode, because positive or negative will remain positive, whatever it is in charging or discharging. efficiency. One of the indicator of the performance of batteries is the efficiency, and the efficiency is the difference in the capacity between the charge and the charge, meaning what I give as electricity and what I recover as electricity. Energy and efficiency, this is the formula that I show this water efficiency because I will talk about the origin of this irreversibility in lithium-ion battery. This is why I'm showing. This is a formula given the maximum power and so on. This is an example of lithium-ion cell. It's a cylindrical cell, and you recognize here the cathode and the anode. Where is the cathode and where is the anode? During the discharge, the anode is negative, and the cathode is positive. Okay? And during the charge, the opposite, but the polarity will remain the same. So, you can recognize here from the color of the current collector. The current collector is the substrate where we put the active material, that we use copper for the negative electrode, and the copper is coated by graphite, and aluminium foil for the positive electrode, and this is coated by the cathode materials, for example, transition metal oxide. Between the two layers, there is a separator, to avoid any contact or direct contact between the two electrodes and avoid short circuit. And the separator will, after being assembled, will be filled by the electrolyte. The electrolyte, which contains the charge carrier, the salt. This is the composition after being dried of the electrode. The electrode, of course, contains the active materials and also a binder that will bind the particle of the active material. Some example of electrolyte using in lithium-ion batteries. Usually organic solvent from this family, alkyl carbonate. Some of them are cyclic, some of them are acyclic, linear. And as you can see in this table, there's many compositions, different compositions. Using the same solvent, but the ratio, different ratio. For example, for the first example, ethylene carbonate, dimethyl carbonate, 50%, 50%. Commercial name LP30. If I take this one, for example, it's a ternary, this time, ethylene carbonate, diethyl carbonate, dimethyl carbonate, and here the composition is the fraction, the mass fraction. And this one is ternary and contains another solvent. This time it's not an alkyl carbonate, it is an acetate. Why? We are using this complicated formulation of the electrolyte for different reasons. To improve or to reduce the viscosity, because ethylene carbonate is very viscous. So to reduce it and to reduce the viscosity, we add another solvent in the same family, alkyl carbonate, but which has low viscosity. Why we need something less viscous? Because it will improve the conductivity of the electrolyte, of course. Why sometimes we are using three solvents, ternary mixture? Because usually the third solvent are added to provide a property that the binary mixture don't have. For example, the functioning at very low temperature, or sometimes, like here, for acetate, this acetate, this family can be added to allow the functioning of the batteries at very low temperature. Melting point here at minus 84 degrees. This one, for example, the AC, ethylene carbonate, is solid at ambient temperature. It's really solid. This is the chemical structure. And the salt. The conventional salt is lithium hexafluorophosphate. once in the solvent is dissociated to Ag plus and hexafluorophosphate minus. There is other alternative salt that can be used, but in terms of cost, the benchmark is still lithium hexafluorophosphate. In terms of chemistry of the materials, of course, there is different cathode materials, different anode materials also. Here I gave some examples. And the difference, of course, the composition. This one is cobalt based. This one manganese based. This one is a mix between different transition metal, cobalt, nickel, manganese, and the idea here is to decrease the amount of cobalt and substitute cobalt by nickel and manganese, which has lower cost. Lithium iron phosphate, lithium manganese phosphate, and now there is a mix between manganese and iron, and lithium manganese iron phosphate that exists also. And so the difference beyond the chemistry, of course, the operational potential. Each electrode operates at different potential, higher or lower. In the anode side, the state of the art is graphite, of course. We can use hard carbons. We can use also silicon, not alone because it's not stable, but companies now are adding 10 to 20% of silicon to graphite to provide more capacity to the anode materials, lithium-ion batteries. This one is very interesting, lithium titanate. It's an oxide of titanium that can be used as alternative anode, alternative to graphite. And the advantage with this is to provide very fast charging and discharging. So for high power lithium-ion battery, this is the material we use. But there is a disadvantage for using this because, as you can see, for the potential, it has higher potential than graphite. So we lose almost 1.5 volt in terms of voltage in the battery. The voltage profile, of course, since we use different cathode material having different voltage with the same anode, then we have a different voltage plateau. Now, lithium-ion beyond the thermodynamic limits. So lithium-ion batteries, most of them are operating beyond the thermodynamic limits of the electrolyte. So the electrolyte between the electrodes should decompose once it's faced to the voltage between the two electrodes in the lithium-ion batteries because it's very high. So why it's not happening? It's not happening because there is a phenomenon that happened during the first charge on the electrode that passivate the electrode and provide stability of the electrolyte against this electrode. Of course, the main advantage in using lithium-ion batteries is this high voltage compared to other aqueous system that works less than 2 volts, so then providing less energy. So this is a figure that shows the first charge and discharge of a lithium-ion battery using cobalt oxide, or lithium cobalt oxide as the cathode material and graphite as anode material. Starting the charge of both electrodes from the open circuit voltage here, in the blue color, the first charge of the graphite. And during the first charge of the graphite, you see that the potential increase. And this happens because you are creating the lithiated graphite, which has a potential close to the lithium metal. So that's why the potential is decreasing until reaching almost zero versus lithium. So it becomes like lithium. have the same potential, almost the same potential. At the same time, during the first charge, the cathode is being oxidized. Then, to compensate this oxidation, lithium is disassociated from the cathode, or from the positive electrode. The green color is corresponding to the full cell, meaning, the positive together with the negative electrode, positive minus negative. This is the profile of the whole battery. This is the profile of the charge of the negative electrode. This is the profile of the charging of the positive electrode. Then during the second, then the discharge starts once the maximum charge is reached. Then we start the discharge, but the total capacity don't return to the beginning. So we have here some loss of the capacity. Okay, and the same for the negative electrode. We will come back during the discharge. I didn't reach the same state as before, as the beginning, and I have some capacity loss. This is the reversible capacity. During the first charge, we lost some capacity at the positive electrode and the negative electrode. When I assemble the full battery, because the picture we have seen, it's full for the negative electrode and the positive electrode. And now for the full cell, what we see on the full cell, this irreversible capacity after the first charge and discharge, we only have as a Coulombic efficiency 86%. Okay, and then the following cycle, this reversibility decreases. So, what is the origin of this reversibility and why it is decreasing? So, as I said before, the lithium-ion battery is operating beyond the thermodynamic stability of the electrolyte. So the electrolyte should decompose. And this is actually what happened during the charge and the discharging, because some component of the electrolyte, some solvent in the electrolyte starts being oxidized at the positive electrode and reduced at the negative electrode. As you can see, reduced getting electron from the anode, negative electrode, and here oxidize it, providing electron to the cathode. And this reaction is not useful for storage, because they are irreversible. But at least for those reactions, they can. The product of this reaction will provide a coating of the material, of the anode material, negative electrode, and for the positive electrode. And this coating, this is what we call the passivation layer. On the anode side, we call it the solid layer interface, and the cathode electrolyte interface. And once it's formed, it will stop the direct reaction, direct contact between the electrolyte and the cathode material and the anode material. Then the irreversible reaction will stop. And if the coating or this passivation layer is efficient, then the reversibility during the following cycle will decrease and will stop. Once formed, this protective layers ensure safe and stable operation of the batteries. It's essential, because if not, if we don't form this protective layer, the decomposition of the electrolyte will continue, and we will consume the electrolyte, and we will increase the resistance, the internal resistance of the battery. So the battery will stop functioning. So we need to allow this functioning beyond the thermodynamic limits of the electrolyte. We need to provide this perfect coating of the anode and the cathode materials, 10 to 15 nanometers. So its impedance is very low, should be very low. And it can ensure then, because it's very thin and ion conductor, can show fast conduction of lithium ion at the interface. And why it's important for the safer use of the batteries? Because inside your batteries you have an electrolyte, which the main component is solvent, and those solvents are very inflammable. So this is a fuel. And if you have a source of heat, external heat or internal heat. External heat, of course, if you heat it externally. And internal heat, what the origin can be, it's a short circuit and internal discharge between the two electrodes. And short circuit can happen if you fall, especially when you are in condition of abuse utilization or very fast charging beyond the condition of utilization of your lithium-ion batteries. You can form some lithium dendrites on the anode side that can grow and can touch the cathode, resulting then in a short circuit that can heat the battery. So you have your fuel, you have your source of heat, externally or internally, and you need oxygen. And the oxygen can come from, or can be released from the cathode. Cathode is an oxide, so it contains oxygen. And cathode can release oxygen, especially when it is overcharged. For example, you destroy the structure, the oxide structure, and then you release some oxygen in the electrolyte. And can understand easily when you have perfect coating of your material with the good CEI, cathode electrolyte interface. Those reactions, the release of oxygen, can be limited or avoided. So it's very, very important for the safety of your batteries. This precipitation layer. And also it's dependent to the battery materials. Usually people say LFP is safer because the thermal runaway in the NMC, nickel manganese cobalt cathode start at 210 when you use cathode LFP, because the oxygen is more difficult to release from LFP, from phosphate material than oxide material, to release the oxygen to direct the link between oxygen and phosphate is difficult, or more difficult than in the oxide material. Then you have less oxygen, and LFP can resist more to the thermal runaway. So it's safer batteries. Solution to this, of course, the cathode interface and the anode interface should be as perfect as possible. And we can also add some additives as a flavor retardant to the electrolyte, so we can make the composition of the electrolyte even more complex by adding those additives. Functional additive, of course, because if you add this phosphazane, for example, it will play a role of flame retardant. We can use some additives that can form more stable and thinner and more robust ACI and CI. Design of new electrolyte, new solvents and new salt and so on. Some salt can also play a functional role in providing this passivation also. So there is many strategies in the formulation of electrolyte. We can also use what we call ionic liquids. This is a kind of molten salt at ambient temperature less than 100 degrees C. So they are liquid at the normal conditions, usually. And then they are salt that can be used without solvent. Because usually why we need solvent to prepare the electrolytes, to dissolve and dissociate the salt. So if the salt is already dissociated in the liquid, we don't need a solvent. So using this as a solvent can then provide more safety, especially because there are no inflammable. Solid electrolyte using solid electrolyte without solvent, polymer or ceramic, or even sometimes some ternary composition having a behavior like a dry electrolyte. For example, here, composition of this salt, ionic liquid. So there is no solvent. Ionic liquid, salt, and the polymer precursor, and then can make those kinds of films. This is the issues and the solution for lithium. What we are expecting for fast, we are looking for fast charging without dendrite formation, because more you charge the battery faster, more you have the risk to generate the dendrite at the anode. Using anode with higher capacity, cathode with higher capacity, cathode free of cobalt without using cobalt, which is a cost material. And some new concept, lithium-free batteries. That means that you have lithium only in the salt, and you are generating your anode in situ during the first charge. So during the first charge, you reduce your lithium plus to form your lithium metals inside the batteries. For the electrolytes, improving the conductivity, the safety, of course, by using alternative solvent or without solvent. All solid state batteries, adding silicon to graphite to increase the capacity of the negative electrode, then to decrease the thickness of your anode materials, and then gaining some whatever per kilogram and per volume also, because you are reducing the thickness of your electrode materials. Replacing even graphite and silicon by lithium itself. And in this time you cannot use liquid electrolyte and to develop, of course, solid electrolyte for those systems. I will do this one. The different chemistry again, giving just an idea about the main chemistry existing as a cathode material for lithium-ion batteries, and develop strategies for the next future. Of course, conventional lithium-ion batteries using the presence of lithium intercalation compound at the cathode and lithium insertion material at the anode. But other concepts are in development, replacing, for example, the active material and the cathode by sulfur. Sulfur as a cathode material can provide very high capacity, but it suffers from the generation of a soluble product that can form what we call the redox shuttle. Polysulfide formed during the charge of the cathode material will be dissolved in the electrolyte and cross through the separator, pass through the separator to the anode electrolyte, being reduced, then again to the cathode, oxidized, and will do this. This va et vient, parce que j'ai pas en anglais. This is what we call it a redox shuttle. And if we look at the table, periodic table, sulfur, the elements and the sulfur oxygen have also can be used as active materials. This time using what we call metal air batteries. Metal air batteries is batteries that use in the anode side. We can use metallic lithium, and the cathode side air batteries, the porous electrode that use as active material oxygen coming from the air. So the electrode is porous. On this side, oxygen can go through and being oxidized or reduce it here. And the other side, you have the functioning of a lithium, normal lithium anode. Aqueous batteries, of course, the concept under development. Some paper dealing with those problems as alternative electrodes. You can read this review we did on highly concentrated electrolyte for electrochemical system, storage system, summarizing all alternative electrolyte free of solvent concept, solvent in salt concept. Paper dealing with improving the performance of the cathode interface by coating the material and reducing the generation of heat during the function of batteries, using flame retardant also. Other papers you can read on alternative batteries to lithium-ion batteries. This one on those one on zinc-ion batteries using zinc as anode material and manganese oxide as cathode material, providing battery with good performance. This is the charge and discharge, more safety, lower cost, and sustainability. Still have time? Huh? And,
Okay, 5 minutes.
5 minutes? Okay. Just to talk a little bit about supercapacitor, because 5 minutes, okay. Supercapacitor, because no one talks about supercapacitor. So, supercapacitor, like batteries, contain 2 electrodes, but in a conventional configuration, the electrodes are not active. They are providing the storage by simply electrostatic interaction between ions in the electrolyte and the electrode being polarized. They are fast, so providing very high power, and by the battery providing very high energy. This is some application that we move forward. Okay, this is the discharging process, and here. So the main family is in supercapacitor. Conventional supercapacitor. This is what we call double layer, electrical double layer capacitor (EDLC). Using carbon-based materials, activated carbon, carbon iron, carbon nanotube, graphene, and so on. This is a configuration, an example what we did a few years ago. For those patents using aligned carbon nanotube on aluminum substrate, and the growth of the nanotube was done by CVD. And the thickness of the layer of the nanotube is 100 micrometer. This configuration allows fast transport of the ions between the channels of the nanotube, then providing very high power and high speed in charge and discharge. This is why we have called this system as ultra-fast supercapacitor. And here an example of performances in using this vertically aligned carbon nanotube materials as material for supercapacitors. This is the energy at different temperature, minus 40 degrees. This is an advantage of supercapacitor by comparison to batteries. Batteries at minus 50, minus 60, up, we stop the functioning. Supercapacitor can operate at minus 40 degrees. And the reason is the electrolyte. So using nanotube, we still keep distant performances even at minus 40 degrees by comparing to conventional activated carbon. This is a picture of this vertically aligned carbon nanotube. We can use as a material pseudo-capacitive materials. Pseudo-capacitive materials is materials that can be oxidized or reduced, so can be the origin of a charge transfer reaction. But those reactions are very fast and usually happen only at the surface, the extreme surface of the materials, usually as a nanoparticle. And most of them can have the behavior of capacitors, so linear response of the potential, not the power, the potential with the time, or a behavior or response of battery, depending on the shape And depending if the reaction is happening only on the top of the surface, the external surface, or on the bulk of the material. Okay? So those materials can be used as a material for supercapacitor, and since they are using charge transfer reaction, we call it pseudo capacitors. This family includes also conducting polymer, famous one, polythiophane, polypyrrole, and polyaniline. Then composite material, we can combine both material, carbon material, especially if we have a very beautiful configuration or geometry, we can coat those material with the pseudo-capacitive material, and then we can improve the capacitance of the materials. This is an example with the vertically aligned carbon nanotube coated with the, by manganese oxide, providing then fast charging and high finished capacitance. Because the next part we start hydrogen and I will not finish. Okay, hydrogen. Thank you.
Okay, thank you very much, Mr. Ghamouss, for this excellent presentation. So we want to just take one or two questions if you have questions. Okay. Just start with
about ionic liquid, which is the specificity of this chemicals for this application.
So ionic liquid is salt, which is dead, usually at ambient temperature. It means ambient temperature can have the salt dissociated in ions that are in the ions without using salt. So usually when you prepare rice, you use solvent dissociate the salt to make it solution-rich, ion-rich solution. Ionic liquid by itself provide you a liquid system with ions only. So for supercapacitor, you can use it without any other salt. And then you store the ions from the ionic liquid. And since you don't have solvent, and the solvent it's what limits the potential usually, then with supercapacitor using ionic liquid, you can reach even 3 or more than 3 volts.
And this ionic liquids enhance the stability of the cell.
If you are
If we compare with other
Yeah,
for example.
yeah, basically ionic liquid will be more stable because it is not contain solvent. So I would say yes. Maybe other reason for your system to be not stable. So there is the material also. So if you regard the material of the electrodes.
Okay, there's another question. I think that we're exhausted. So thank you again, Mr.